Hello class, welcome to this lecture about how the Earth was made. I hope everything's going well for you guys today and that you are ready to learn about this very exciting process. This was also on our pre-test. It was our first question, so our step one of how the Earth was made was actually the universe was created. It was also known as the Big Bang. So we have that the Big Bang occurred about 13.8 million years ago. At this time, or like right before I should say, material was just kind of around. It was moving around in space and just slowly there. And then we have this very large bang, which puts a lot of energy into space. And now we have these materials moving quickly, and then they start to collide and collect, bump into each other and group together. So what we believe happened is the Big Bang happened about 13.8 billion years. There's about 0.8 billion years of things running into each other before stars were formed. And then we have another 8 billion years before our own sun is created. So our evidence for this is we can look at the material in the outer space that is still around today and determine that those materials that are floating around are actually within our stars and within each planet. So step one is the creation of the universe, which is also known as the Big Bang. Step two, we have layer formation and differentiation. So let's break down some of these words because they're a little bit big. So layer formation is just the process of creating unique layers. So there might be, for example, on a cake, we have the cake part and then the frosting part. So those are two different layers, and the differentiation is that they're different, right? So the cake part does not taste the same as the frosting. They are completely different substances. But right at this time, the Earth is still kind of being made. We have a kind of a softball of rock, which I think a good way to think about it is maybe we have a kind of soupy bit of mud. We have a mud that has a lot of water in it, and it's just kind of running out of our hand. But as we kind of push it together into a ball and squeeze out that water, it gets to be really hard and dense. And that's kind of how the Earth happened. The collisions of other objects, other rocks flying around in the outer space, forced the dense material to go into the center of the Earth, into this very inner core. So all our dense material moved there. Also, it's around this time that the moon was made, and that was made by a large rock hitting the edge of the Earth and forcing a chunk to float off, and that chunk is known as our moon today. So thankfully there was lots of collisions, otherwise we wouldn't have a pretty moon to look at night. And our evidence for this is our layers of the Earth. So on the picture to the right, we can see we have our inner core, which is the most dense material. Then we have our outer core, which is a little bit more like magma, but still pretty hard. And then this mantle, which is all magma. It's moving around. It's very thick, but it is still a liquid. And then our outer crust. Now, you might be wondering how we know this, because we can't drill into the center of the Earth. There's no way to do that. And so how scientists have done it is they use what is called an ultrasound. An ultrasound is also used to look at babies when a mom is pregnant. And the way it works is it shoots sound waves into the stomach, or if we're looking at the Earth, from the crust into the center. And as it goes through different layers, different reflections of that sound wave come back to the instrument. So it's a really cool technology that allows us to see. Step 3 is cratering and impacts. So as asteroids and other objects hit the Earth, craters were made. We already have our pretty distinguished Earth at this point, pretty solid ball of rock as our Earth right now. But there's still a lot of things flying around in space. A lot of craters are being made. And as these craters were created, some cracks in the crust happened, which would start our next step. But how do we know there were some craters? Well, we can look at other planets that are close to us in our solar system, or even our moon. So Mercury, Venus, and Mars, as well as our moon, have noticeable craters still on them. So it is easy for us to speculate, to think, to guess that our Earth would also have similar craters if it weren't for our next few steps. Yes, so we can't see our craters today because of lava flooding. So as those cracks in the Earth formed or were opened, the magma in our mantle released, and then the lava went and filled in all those craters, just like water does. Just like water will kind of run to the lowest point of a surface. Maybe you have been mopping before and you notice that the water likes to puddle along the wall or puddle maybe in the middle of the floor. That's the lowest point. Our lava did the same thing and ran to the bottom of those craters and then slowly filled them up until we had a pretty smooth surface. So, what is our evidence? Well, we can still see volcanoes erupting today. So we can still see this lava happening, especially around Hawaii. There are lots of active volcanoes still. Really, across the world, there are a lot of active volcanoes. So step 4 is lava flooding. Step 5, we have surface evolution and change. So once we have our craters filled in, then the plate tectonics will move together and collide with one another. And I believe you guys have learned this before, but I just want to go over a quick review of plate tectonics. So we have different collision types which result in different landscapes, and Earth was pretty much done forming around this time. And this process, this step 5, surface evolution, is still going on today. So our 3 main types of collisions are divergent, convergent, and transform. So divergent means that they're going away from each other. They're spreading out, as you can see in these arrows, and it creates this ridge. So this fancy word lithosphere is part of our crust, and our asthenosphere is the magma mantle. So the magma wants to push through this crater, this ridge that is going on, and will form new land. Then we have our convergent, which has a subduction zone. So subduction means that one plate is going underneath another. As you can see, this plate on the right is going under the plate on the left. It ends up creating a trench, and we actually lose part of the crust. Now, this crust that goes underneath will be heated up by the magma and reused in another area like a ridge. But in this specific instance, we are losing part of our Earth, part of our crust. Now, it creates a nice trench, which has a lot of earthquakes, as you can see by these stars, because there's a lot of energy and friction between those two tectonic plates. It also creates an interesting thing of volcanoes. So we can see volcanoes on the side that is not being pushed under. Our final way that plate tectonics interact is by transform collisions. So this is a lateral sliding. You can almost think like if you had two pieces of paper side by side and push them apart, or maybe even two books, something a little thicker, they might want to grip together. So there's no major loss or gain of our crust and no volcanoes, but earthquakes can happen along this edge because there is that friction and that energy right there. So this isn't a great picture, but these are all of our plates, all of our tectonic plates, which are also from around the world. So we have a Pacific plate, a North American, Euro-Asian, African, South African, Australian, and that we can see these interactions are all those, one of those three that we just went over. So going on to kind of our next topic, we are going to start talking about what happened to create life. But before we get into that, I want to ask what is something what is needed for something to live, for anything to live. So let's start by thinking about us. So we need shelter. If we're left out in the heat for our whole lives, we will get dehydrated and possibly die. We need food, otherwise we will starve. We need water, otherwise we will become dehydrated. We need a lot of water, actually, and we need some space to live. If we have no space to live, then we're just kind of nowhere. So for anything, more generally, shelter becomes just a safe environment. We need materials as food. Not everything uses the same kind of food we do, so we just need some materials. Energy, and of course water. We always need water. So where does this water come from on the earth? We didn't talk about that in any one of our stages of earth creation. So we honestly are a little unsure. Unsure about this, but we have some good theories. But we can't quite prove anything for sure. Our first theory is during the release of lava, water vapor was also released. So water vapor is water in the form of a gas, and that is thought to have gone into our atmosphere, condensed, and then rained and filled all our oceans with water. So that's one idea. Another idea is that water was brought in the form of ice when asteroids were hitting the Earth. And then once on Earth, it was at a warm enough temperature to melt from ice into liquid water, and then we had a normal water cycle where Earth heated up the water, it was condensed, and then rained again. So which do you think is most likely to happen? Either way, we know that water was around, but these are just the two possible theories of which they happened. I like to think theory one is a little bit more logical, but it is all up to each one of us to determine what we believe. So, thank you. I hope this lecture was clear. If you have any questions, as always, please let me know.